and welcome to AstroPod, the astronomy podcast series conducted by the Astronomy Club of the University of Sri Jayawardenepura. We are delighted to have you with us once again as we continue our journey through the wonders of the universe, exploring fascinating ideas and discoveries in space science. For today's episode, we are truly honored to be joined by an outstanding astrophysicist and planetary scientist, Dr. Nalin Samarasinha. Dr. Samarasinha is a senior scientist at the Planetary Science Institute in Arizona, USA, where he has made significant contributions to the study of small bodies in the solar system, particularly comets and asteroids. His research focuses on their rotational dynamics, evaluation, and physical properties, helping us better understand the origins and behavior of these celestial objects. Over the years, Dr. Samarasinha has been actively involved in numerous international research collaborations and space science missions, and his work has played an important role in advancing planetary science. His expertise and dedication to the field have earned him recognition within the global scientific community. We are incredibly excited to have him with us today to share his knowledge and insights into planetary science, comets, and the broader mysteries of our solar system. Joining me today as our host, Ms. Kulamini Amarathunge, who will be leading this discussion and guiding us through what promises to be an engaging and insightful conversation. So once again, welcome Dr. Samarasinha, and it's a pleasure to have you with us today. And to our host, over to you.
Yes, thank you, Sonagi. And thank you, Dr. Nalin, for joining us here today. And so today we're discussing...
Thank you very much for inviting me, and thanks for the introduction, Sonagi, and also for the Astronomy Club at Sri Jayawardenepura University.
Yeah, so today we're discussing planetary science, not only the planets themselves, but also the broader processes that shape the solar system, including smaller bodies like, comets and asteroids and whatnot. And I think what makes planetary science especially interesting is that it sits at the intersection of many disciplines. Like, for example, it has astronomy, geology, chemistry, physics, and even atmospheric science in it. So I think maybe that's a good place to begin. So when people hear the term planetary science, they often think it's just about studying planets individually. But as I understand it, the field is very much broader than that. It includes planetary formation, atmospheres, surface evolution, internal structure, moons, asteroids, and even comets. So, from your perspective, how should we really think about planetary science as a discipline, and what kinds of scientific questions is it trying to answer today's world?
Thank you, Kulamini. 100% correct. It's a multidisciplinary subject, and by the way, astronomy nowadays itself is a multidisciplinary subject. Of course, the most foundational subject area is physics. But one thing I want to mention, when we study at school or at a university, we have different subjects: physics, chemistry, mathematics, etc. But the real life is not compartmentalized like that. So you have to have these different branches. And another subject which is of great relevance is computer science, especially the computational methods, and now AI, machine learning, and all those things come into play. So, this is true for astronomy as well as planetary science. When you take planetary science itself, there are a lot of people who came from astronomy side, like myself. My postgraduate work was in astronomy, and bachelor's, the first degree was in physics. And at the same time, there are certain planetary scientists, they are planetary geologists, because especially now as well as few decades back, we have spacecraft visiting other planets, asteroids, comets. So to fully understand the physical processes going on there, you need to have that geology and geophysics knowledge. So in that sense, there are a lot of planetary geologists. And sometimes they do comparative geology. And of course, certain things are not exactly like what we find on Earth. For example, erosional processes, if we take on Earth, is different because wind, for example, have a lot of erosional processes, whereas some objects in our solar systems, they might not have a atmosphere like Earth, or basically almost atmosphereless, like if you take like Moon, for example, or asteroids. So all those expertise are needed. That doesn't mean each person needs to have all those expertise, but I mean, nowadays, especially the spacecraft missions, there are a lot of scientists involved in. So the group who is working on, they have people with different expertise. So whether it is computational technique, whether it is geology, or whether it is chemistry, and sometimes even biology. But if one wants to be a planetary scientist, I would say probably physics is the most relevant subject. So you need to have that basic physics background. And another thing which I should mention, one thing that all other branches of astronomy do not have, but planetary scientists have, is the ability to visit the objects. Or sometimes you can even do an experiment by going there. So that added advantage is there. So there are a number of Sri Lankan origin astronomers, planetary scientists, planetary geologists. In the world, unfortunately, most outside of Sri Lanka. But the opportunities are there if you are really interested and you have your goals, and if you are determined to work towards your goals.
Yeah, thank you, sir. So, about the formation of the solar system, I've heard many theories about the formation of the solar system. Are they actually evidence-based? Is there like one theory that we can say, okay, this is how the solar system was formed?
Yeah, the leading theory is the solar system was formed from a huge gas of molecular cloud. And there was some external trigger, which we don't know for sure, that started collapsing. And when that started collapsing, because in physics, we have what we call conservation of angular momentum, that you can think of as the amount of spin. So the amount of spin will depend on the extent of the object as well as the rate at which that object rotates. So this molecular cloud, when it started contracting, it started to spin faster and faster. So this is essentially a gas cloud. When I say gas, it is gas and dust. So basically, these were gas and dust originally, long time back, produced by other stars when those stars died. Then when it started rotating faster and faster, it got flattened. Just think of somebody trying to make a clay pot or something like that. So it's like exactly that kind of, it get flattened out. So at the center, you have most of the mass. The sun was formed. And then further out, you have planets forming. And the planets which were formed close to the sun, they were mostly solid rocky objects. And further out, like the giant planets of the solar system, Jupiter, Saturn, Uranus, and Neptune, those are gaseous planets. And before the planets form, during the contraction process, the building blocks were formed. So the building blocks were the asteroids close by, primarily, and further out, comets. So you can think of as the objects, the planets which form close by to the sun, they were formed by accumulating small asteroids, and further out, comets. And so that is why if you look at the gas giants, there is primarily you will have gases. And so this was consistent with this hypothesis is consistent with the observational facts. For example, if you look at the solar system, almost all the planets are confined to a plane. I'm not counting Pluto, and Mercury has little inclination, but others, the inclination between the other planets, only few degrees. So that explains, that observational fact is explained by this hypothesis. And actually, there are so many stellar nurseries like Orion Nebula, where the new stars are being formed at this time. And there may be planets forming around those stars. So that is the leading theory, and out of the many that you mentioned. So that is pretty consistent with the observational evidence.
Yeah, I was actually, my next question was the diversity, like how these planets diverse from each other. Actually, you answered that question as well.
Okay.
So my next question is, are they evolving over time? The planets, like for an example, let's say Mars, Venus, Earth, they may have started with some similarities, but today they are completely different. Like they have completely different environments. So, what do comparative studies of planets tell us about this planetary evolution and habitability of these planets?
Yeah, it's a very good question. It evolved from a geological point of view as well as from a dynamical point of view. So first I will talk about the dynamical point of view. So all these things we learned last 20, 30 years, basically, or 35, whatever. So basically one generation. And when the solar system was formed, the planets that we have, especially Jupiter, Saturn, Uranus, and Neptune, they were not in their current locations. They migrated inward or outward. So the planetary migration is apparently a very common phenomena, and astronomers have invoked planetary migration to study or explain the observations of other planets around other stars, exoplanetary systems. So, for example, if you take Jupiter, Jupiter has an orbital period of about 12 years. I'm just giving the rough numbers. And Saturn has about 30 years. So 12 and 30. So when Jupiter goes around the sun twice, Saturn goes around Jupiter goes around the sun 5 times, Saturn goes around the sun twice. So we call it 5-to-2 orbital resonance. So then if you look beyond Neptune, Pluto, for example, Pluto is, from a dynamical point of view, is not a planet, but in a moment I will tell from a geological point of view, it is a planet. So Neptune and Pluto, they are in what we call 3-to-2 resonance. So that means when Neptune goes around the sun 3 times, Pluto goes around the sun twice. So they're dynamically connected. So they are called dynamical resonances. There are a lot of dynamical resonances in the among the trans-Neptunian objects. That means the object beyond Neptune. There are more than 5,000 objects that we know of. The first one, if you ignore the Pluto system, was discovered in 1992. So basically, I was just out of graduate school at that time. So 8 plus 26, last 34 years, we know of more than 5,000 objects, but orbits, pretty well-established orbits. That means that is when an object is numbered, probably around 1,000. So that is from a dynamical point of view. And then from a geological point of view, we don't even have to go and look at other planets. If you look at Earth itself, Earth's early atmosphere was not conducive for life to start or evolve. But it evolved with time. And so geological processes, volcanoes, interaction with sunlight, sometimes plate tectonics. All those processes cause geologic activities, which basically all the planets in the solar system, they have undergone evolution throughout its solar system's history of 4.6 billion years.
Yeah.
If I may add something,
Yes.
I mentioned that probably this is a question you may even ask me later, but I told that asteroids can be think of as building blocks of rocky planets, and comets as building blocks of giant planets. And of course, there were many more during the very early stage of the solar system, even after the planets were formed. And so still, even though the planets have evolved a lot, asteroids and comets, they are the least evolved objects. Like 30, 40 years back, a lot of astronomers used to say they are almost primordial. Actually, that is not 100% right. There was some evolution because, for example, if you take the current asteroid in the asteroid belt, for example, there were collisional products because asteroids collided over last 4.6 billion years, but less collisions with respect to comets, but comets are in the cosmic ray environment, so at least the top layers of comets may have had certain chemical alterations, so to speak, from that primordial state. Okay.
Yeah, so that means like we can describe these comets as remnants from the early solar system, I think, as I understand it, because they
Yes.
formed like very far from the sun and remained relatively unchanged, as you mentioned. So they somewhat preserve information about the early solar system that planets may no longer even contain. I think it creates a picture scientifically. Do you think that it is accurate? Like, do they
Yes,
actually?
definitely. So actually, when we try to justify why we study comets, that is one of the reasons, because we can go back 4.6 billion years and we can see what the conditions were. For example, chemical composition, what kind of environment that they were formed. Those things can be studied by studying comets. And so, again, I want to stress the fact there were a certain amount of evolution, especially in the outer layers of comets, but by far, that is the best preserved, if you want to use the word fossils, from the past. So I would say that. And of course, there are other advantages of studying comets. Comets brought, and asteroids, of course, brought both water and organic matter to Earth. So probably that may have helped origin of life on Earth. So those complex carbonic molecule and complex organic molecules, and water, of course.
So one more thing, so about comets. When they approach the sun, we see the coma and tails forming due to the solar heating and outgassing. So but beyond the visual aspect of it, what kind of scientific information are researchers actually extracting from comet observations?
Except for, I think, a handful of comets, because it is very difficult to see the nucleus of a comet. So nucleus is where all the secrets are hidden, so to speak. When a comet comes closer to the sun, typically around even 4, 5, or sometimes even more than that, astronomical units from the sun. So 5.2 AU is where Jupiter is. So even at that distance, it is not water. Some of the other gases can sublimate. So water sublimation happens, it picks up very fast, around 2 to 3 astronomical units. And so when a coma is formed, it will obscure the nucleus. So most of the observational evidence on the nucleus is derived from what we observe in the coma. Some comets can be weakly active, very far away. The problem is when they are very far away, say at Jupiter distance or even further, they are really, really dim. So you need very large telescopes to observe. And there are few other comets that humans have sent spacecraft to. Most are flyby missions, except one, the Rosetta mission to comet Churyumov-Gerasimenko, which was an orbiting mission. We didn't have a clear snapshot of the nucleus. So by studying the coma, by taking the spectra, we can find out what molecular species are there, and what are their abundances. So if you take the gases, of course, water is the primary, in the form of water ice in the nucleus. That is the primary ice. And then you have COO, CO2, carbon monoxide or carbon dioxide, depending on the comet. So I'm talking in general over all the comets that we have observed. So there is funny thing that if you want to observe water, you can't observe in visible range. You have to go to infrared, for example. And there are a lot of other molecules where you can observe in infrared. So from Earth, it is a challenging task because of Earth's atmosphere. So most of the species that we can see are what are called chemical radicals. So I will give some examples. It is hard to make in the lab. So if you are a chemistry fan, One is a CN molecule. It is a radical. So for example, if you take hydrogen cyanide, if you break hydrogen and CN, so you get a CN molecule. And then there is C3, 3 carbon atoms. Then C2, actually, most of these are produced by photodissociation. That means sunlight falling onto a molecule and they break. And there is OH. So that is primarily breaking water into OH and H. So if you take, if you won't mind, I assume most of the audience is university level. So now if you take OH, the atomic weight is 16 and H is 1. So OH is 17 and H, because when you break water into H and OH, H is just 1 atomic mass unit, OH is 17. So you had, when a photon comes and breaks that, photodissociation, you had to have the conservation of linear momentum. So that means, so the water molecule coming out from the comet, you break that, and so the hydrogen molecules move 17 times the velocity of OH molecule. So if you take an image of a comet sensitive to hydrogen, you will see a huge hydrogen coma. So whereas OH coma is much smaller. But OH can be observed. It's actually around 3100 angstrom in the blue region. So again, it can get affected with Earth's atmosphere. So you need to have a good location. So all the major species that you see invisible, they are chemical radicals. So even a chemist has something to think about.
Yeah. So it's actually very amazing to think about these things because like it feels like everything is interconnected. If
Yeah,
you think about
certainly. Yeah.
yeah. So
The natural world is like that.
exactly.
We break into different regimes because it is easier to study those, but the natural world is like that.
Yeah.
I mean, you don't have to be an expert in all those fields to study, be an astronomer or a planetary scientist. You have to have your own specialization, but you have to have a basic understanding of these other areas.
Yeah. So when you talked about how we have found how we have used spacecraft images and telescopes to find out these things about these comets and everything, I think in modern planetary science we have a heavy dependence on data analysis, simulations, and spectroscopy and whatnot, remote sensing, even modeling, I think. So what does the actual research process look like today in this world?
Yeah, like you said, it involves all those things. And when I was starting my graduate studies, which was more than 40 years back, I think none of you were born at that time. So before that, it was photographic plates. So you take a photographic plate and you expose to the image, and then you have to develop in the dark rooms. So in fact, I have gone through that learning process, but in the 1980s, that is when I started, CCDs came. So the main advantage is you don't have to go through all those things. Even though I learned how to develop the photographic plate, since CCDs came, now, of course, you can see in many cameras, for example. Actually, astronomy is one area where CCD cameras were first used. Those cameras were rejects, which are not suitable for certain other stuff. So, of course, you then do the calibrations and stuff like that, and you take the image, and so it is a much easier process, and also CCDs, the response to light, unlike a photographic plate, is linear. So that means if you double the if you observe an object which is twice bright, the signal that you have will be twice. But photographic plate is not like that. So then, of course, computers, especially you have to write your codes, and now probably ChatGPT might do it but still, you should not be a slave. You should use whatever AI technique as a slave of you rather than you being a slave. And because even a computer, it will give results based on what we ask it to do. So you have to ask the right questions. So computational technique is a huge thing, and all the other things that you mentioned.
Yeah, so I think one important discussion is, especially for students listening from Sri Lanka, is accessibility, because planetary science can sometimes feel very distant, almost like something only possible in countries like where they have space agencies, major space agencies. So realistically, how can a student from a country like Sri Lanka begin entering this field?
Okay, good question. I will give a very general answer. The reason is I can tell my path, but my path is not the only path. So I did physics special, and then came to US and did PhD in astronomy. And so basically the astronomy side of comets. So this was the time that comet Halley's last apparition, 1986. Actually now Halley has passed its aphelion and it is coming back. So all you guys should be able to see it in 1961. Probably I may not be there unless I'm more than 100 years. So that is how I did it. But as I said, physics background, you don't need to even do physics special. I mean, there are a lot of others, both astronomy as well as planetary science, people who have done PhDs in both of those fields. They have done even the general degree. But you have to have the dedication. You should be able to make certain compromises. It's a lot of work. And I mean, I don't know any astronomer who is starving, because there is a joke, there are starving artists, but there are no starving astronomers. They may not be really rich, but you get to do what you like to do, even if you can't find a job. You will have a skill set which you can use those skills. So, for example, I know some astronomers and planetary scientists. They have gone to Wall Street, that means financial markets, doing modeling, financial modeling. Then people who are working, again, modeling in banks. Then people who have done big data aspects of astronomy. They have gone to do big data projects, nothing to do with astronomy. So there are and the computational skills. You have the analytical skills. So those skills are marketable in areas where you are not even think of. So that is an advantage. So as far as getting into do a graduate program, especially those days, I did physics GRE, and now, at least for students from the US, it is not mandatory. But if you have done physics GRE and if you have a good score, it will be a way of convincing, especially if the particular university a student is applying is not familiar with the university the student got his or her undergraduate degree. So that will help a lot. And especially planetary science, it will help some geology background. In fact, I know a few Sri Lankan planetary scientists who had a geology background. The one that I'm thinking of, his first degree was in geology from University of Peradeniya. So that way, don't think, oh, this is something I don't have to, I can't do, or hard. But at the same time, you have to be realistic. You have to work hard. And I will tell another Sri Lankan colleague, much younger than me, who has done his first degree in a South Asian country. Sorry, a Southeast Asian country. And then went to France and did his PhD there. And still he's doing research. So, and also something I should mention, I told how the images were taken when I entered the field and how it was different few years later. And things have changed a lot. And so now there are a lot of space missions, and even some of the telescopes like Vera Rubin Observatory, the LSST survey. So which is going to start soon, to scan the sky. And so those projects involve a lot of astronomers. So it is a group effort. So if you go back 1 or 2 generations before me, there were people who were working on different branches of astronomy at the same time. But things have changed. So always open to challenges and the changing landscape of the field. I shouldn't say landscape of the field, I mean, the entire world for that matter. So you may need to learn new skills. So that is always the case. Probably not 100 years before I went to grad school, but but certainly now.
Yeah, so I think what we must understand is that beyond becoming a researcher, there are also many related career pathways that we can get into by studying this field. So when we look ahead, planetary science seems to be entering a very exciting phase, especially with new missions, improved telescopes that we're using nowadays, and growing interest in habitability and life beyond the Earth. So this is a question that I ask from all the podcast guests. From your perspective, what are the most important unanswered questions in planetary science right now?
Okay. If I take a minute before answering that question, I should mention I recently got to know of a Sri Lankan origin planetary scientist who is even working in United Arab Emirates, because UAE has I think they are having a moon mission, and so there are opportunities even in other areas. So not only in the US, so there are a lot of other places. So the question you asked, what I would like to know? Okay, it is a very broad question. So there are a lot of things. So I will confine my answer to comet studies. One thing, there are multiple answers. And the second thing, I should answer something which is really that I like to know. If we can send spacecraft or multiple spacecraft to a comet with radar capability and orbit it and measure the 3D structure of the object. Actually, Rosetta mission was planning that, but the lander had an issue. So because of that, they could not completely accomplish all they planned. It was only partially they were able to accomplish. So are there some layering, for example? Are there any voids inside? Which might facilitate gas transport, and also to learn how the thermal wave, when the sunlight falls on, how the thermal wave propagate inside. So all those things. And then, of course, probably the same spacecraft has a lander, and ideally much further down, drill and 10 meters or something like that, and get a ice sample, ice, and it is actually a mixture of dust and ice, I would say. In comets, there is actually more dust than ice. So a sample, and this is ice which is at a very low temperature. So you have to bring it cryogenically. That means you have to freeze it. Uh, uh, so if you bring and then you can analyze what is it and understand what kind of evolution, thermal evolution, which especially has occurred, and what is the form of water ice. Is it in like a cage? It's called clathrates. So with the ice is in like a cage where so the other gases are inside that cage. So what it is basically to learn more. So that's what I would like. But it is a very narrow area with my own biases, of course.
Yeah, that's a really great answer, actually. I mean, that would be amazing if we can do that. And yeah, so
I'm pretty sure one day,
we will be able to.
maybe not 10 years, maybe next 50 years,
Yeah.
we can do that.
Yeah, hopefully we'll get there, I guess. So, yeah, thank you so much, sir. This has been a really insightful discussion. So, I think what makes planetary science especially fascinating is that it connects so many different areas, as you mentioned, of science, while also helping us understand Earth's place within a much larger planetary context. And I think discussions like this also like show students that space science is not as unreachable as it may seem, because we think of it as something impossible that we can't reach, but it is actually not like that. It's a field built on curiosity, collaboration, and interdisciplinary thinking. So thank you so much, Dr. Nalin, for joining.
If I may add on that point, actually learning now, there are multiple missions going to go to Venus, and Venus is considered like the sister planet. Things have gone wrong compared with Earth. I mean, you can't live there, but doing comparative planetology and understanding is really important to know where things, to what extent we might have issues if Earth's climate and etc. change, for example. And in that sense, I would like to tell, when I talk, I like to talk with comparative scaling. So I don't know whether you know, but if you think Earth is of the size of a basketball, the Earth's atmosphere is the thickness of this paper. Because the scale height or the e-folding scale, that means the natural logarithm, it's about 8 or 9 kilometers, whereas Earth's diameter is about 13,000 kilometers. So the ratio is like 1,500, but astronomers always like to think in terms of round numbers. It doesn't really matter to explain. 1,000 is good. You don't have to think about 1,400 or 1,500. So, and also I have heard the example of if the Earth is size of an apple, the atmosphere is the thickness of the skin of the apple. So you will see how fragile, so to speak, but it provides a lot of protection from cosmic rays and objects which are falling to Earth and all those things. So that atmosphere. So that is a thought that I want to share with if you are not familiar with.
Yeah, that is a really good example for us to understand how fragile that is. And I think as people, as humans, we all have a responsibility to preserve everything that is here on Earth, and we should focus on that, I think, even more than what we do right now. So yeah, thank you so much, sir. This has been really insightful, and I think most of the people in the audience have might have learned so many things from you, and even I did. I understood a lot of things that I couldn't understand before, and I learned so many things. So thank you again for joining us and sharing your insights with us today. So over to you, Sanugi.
Yeah, thank you for inviting me.
Okay, so that was a really interesting session, I would say. So, as we come to the end of today's episode, we would like to extend our sincere thanks to everyone who joined us for this insightful and engaging discussion. So, most importantly, a heartfelt thank you to our guest speaker, Dr. Nalin Samarasinha, Senior Scientist at the Planetary Science Institute. And dear sir, we are truly grateful for the time you shared with us today and for the incredible work you continue to do in advancing our understanding of planetary science, and your insights into comets, asteroids, and even the dynamic processes that shape our solar system have been both enlightening and inspiring as well. So it has truly been a pleasure having you on AstroPod today. And at the same time, our special thanks also go to Professor MLC Artigala, our senior club advisor, for her continued guidance and mentorship. And at the same time, we are truly deeply thankful to Dr. S. Kandipan, our senior club treasurer, for her valuable guidance and at the same time her continuous support as well. And then in addition, we also extend our sincere appreciation to Dr. R.A.D.D. Dharmasiri, our academic and inter-university advisor as well. And at the same time, we would also like to thank our wonderful host, Miss Kulamini Amarathunge, for leading today's discussion so thoughtfully and making this session both engaging and insightful. So finally, our gratitude goes to everyone who worked behind the scenes and at the same time in front of the camera to make these episodes such a success. And we hope today's discussion has sparked your curiosity and inspired you to continue exploring the mysteries of the universe. And with that, we conclude today's episode. Thank you once again for joining us, and we look forward to welcoming you to our next episode of AstroPod. Goodbye, everyone.